And now we're going to go for an example. And I'm going to work through an example, which is this one, about this guy called Kaito who grows tomatoes. And again, this example is also from Khan Academy. I guess you guys have noticed that I really like uh, their statistics course. And I think they're great. So what happens here is that this guy grows tomatoes in two separate fields. I'm gonna arrange here for me to draw on the screen so that we can do this thing together. But as a summary, as you can see, this guy grows tomatoes in two separate fields. So basically he has tomato plants in two different places, right? And when the tomatoes are ready to be picked, he is curious as to whether the size of his tomato plants differ between the two fields. So that is a very standard kind of like of test where you're saying I have these two different samples that I'm taking from these two different populations, like field A and field B, and I took samples of them, and I just want to compare them. I want to know, well, are they the same or not? And just by observing it, you can very clearly see that the mean of field B is actually larger than the mean of field A, right? So you can see 1.6 is larger than 1.3, but as we've been seeing with statistics, it's never that easy. So I cannot just say, yeah, the mean is larger, so by conclusion, the tomato plants from field B are larger than from field A. I cannot just conclude that because there's variance, right? There's a lot of variance in the measurements. So it could be that this observed difference is simply due to random chance. It could be, and that's what we test when we test when we do hypothesis tests. We're testing whether the difference that we're seeing is actually significant or if it's just due to random chance. And then he took these two samples. You can see the standard deviations of these two samples are also different. So field A has more standard deviation than field B, so it varies more than field B. And also the sample sizes are different, 22 and 24. And we're going to do this. So let me actually, I'm going to start a new whiteboard here. And the first thing I'm going to do is I'm going to repeat some of the information from the that we already have in the example here. So we have, I'm just repeat them in a more like technical way. So we have the sample mean of field A, which is 1.3. We have the sample mean of field B, which is 1.6. And we have the sample standard deviation of A, which is 0.5. And we have the sample standard deviation of B, which is 0.3. And also the size of sample A, which is 22, and the size of sample B, which is 24, right? So we have these information. This is given to us. One thing that's not given here is the significance level. I'll call it alpha. That's not given because we're supposed to just set it ourselves. So I will just set it at 0.05. So I'm ready to reject my null hypothesis if if the probability of my observed difference is less than 5%, given the null hypothesis. And I'm also going to say that the test here is two-tailed, because if we read it, it says he is curious as to whether the sizes of his tomato plants differ between the two fields. He's not saying that he's curious to see if the plants from field B are larger than from field A or vice versa. He just says, I want to know if they're different. And so by consequence, we will do a two-tailed test. Okay. Now, where will we start here? Well, we might as well simply start by actually computing the basics of the sampling distributions, right? So for example, well, actually, there's one thing that we can define here, which is our null hypothesis, but that is very easy, right? My null hypothesis is that the difference between them is actually zero. as always, right? And the reason why I'm putting xb minus xa here, that it's exactly the same if you do opposite. Xa minus xb makes absolutely no difference. It's just that xb is a little bit larger than xa, so this will give us a positive value. But it makes absolutely no difference if you do xa minus xb. You will have the exact same value but negative. And then it's just that then the test will, well, in this case it's two tails, so it doesn't matter at all. But I'm just doing it like this because we end up with a positive value, so that is a little bit easier. But this is our null hypothesis. And then, so we start by computing the actual basic information for building the sampling distribution. So for example, let's call x, well, if we take xa minus x, sorry, actually it was the opposite, right? So if you take xb minus xa, let's say I will call you, just to make it easier, I will call it the x diff, or the difference in the sample means, which is basically then 1.6 minus 1.3, and that is 0.3. So that is our observed difference. That's the value that we observed. That's the value that we're going to test against our null hypothesis of 0. And then I will compute also the, or calculate also the the standard error of the difference, right? Which I will also call it as diff. And this is that crazy computation that we saw before, which was during the confidence interval video. So if you don't know that, please take a look at the previous video. And this is basically the sample standard deviation of, let's say, of b squared divided by the sample size of b plus the sample standard deviation of a squared divided by the sample size of a, and then we take the square root of the whole thing, right? And for this, of course, I will end up using a calculator, but it's initially the computation is not that hard. So basically this is 0.25 because it's 0.5 squared divided by the, or sorry, I'm doing the opposite here. We start with sample B. So sample B is 0.09 because that's 0.3 squared. Then the sample size of B is 24 plus the sample size of A squared, which is 0. I'll do it a little bit, yeah, 0.25 divided by 22, which is the sample size of A. And then we take the square root of this. And this will be approximately something that I will actually calculate right now very quickly. So let's see, 0.09 divided by 24 is 0.00375. And 0.25 divided by 22 is a big thing. So it's, let's just say it's something close to 0.01136. So let's stick with 5 decimals here, 0.1136, yeah. And then I will take the square root of this. Then again, this is what? Let's see, 0.00375 plus, sorry, 0.00375 plus 0.01136, which is 0.01511. So, and then I'll just take the square root of that because why not? So then that gives us something close to 0.12292. Okay, so this is our standard error. Great. Now then, so basically we have the basic information here. We have our observed value and we have our sample standard error here. Not standard error, the standard error. Now the next thing I'm going to compute then is the actual t statistic, right? So the t statistic, as we saw before, is like taking our observed value and putting it into the sampling distribution, which is 0.3 divided by 0.12292. And if you don't understand why I'm doing this, please take a look at the slides, because this is basically the observed difference divided by the standard error. And we saw this on the slides. And again, of course, I don't know this, so I will do it in the calculator. And that gives me something close to 2.44 with some other numbers, but it doesn't matter. It's very close to 2.44. So our test statistic here is 2.44. And basically what this means, well, this means that this specific observed value, 0.3, is 2.44 standard errors away from the mean, to the right, because it's positive. So that's kind of like, that's an indication that maybe we're going to reject our hypothesis, because as we saw before, usually 2.44 standard errors away from the mean, that's usually a very extreme value, right? We usually go up to 2 point something at most, but 2.44 looks like a very extreme value. It looks like it's quite many standard errors away from the mean, so it kind of looks like a rejection. But let's confirm. Let's see. And in order to confirm this, we're gonna compute our t star, right? So I'm gonna make it all the way over here so we can compare. And what's our t star? Well, our t star is going to be computed using some kind of online calculator here, which I'm going to do this somewhere here. Just I won't be able to share this in the screen, because then I would lose my drawing if I do that. So I won't do that. But I'm going to use the same calculator that we used during the examples. So I'm just going to say my significance level here in this case, I'm going to put 2.5%, right? Because actually it's 5%, but it's two-tailed. And the calculator here that I'm using is fixed at one tail. So I'm using 2.5. And what are my degrees of freedom? Actually, I forgot to put that here. My degrees of freedom are actually 21, right? Because 22 is my smaller sample, and 22 minus 1 is 21. So this is my degree of freedom, 21. So I'm going to put here 21. And that gives me a critical value of 2.08. Well, that 8 was horrible. 2.08. This is my critical value. So immediately you can see that we are going to reject our hypothesis. And we can actually just do that, because we can say, okay, t is larger than t star. Or in this case, larger means more extreme, because we're looking to the right. We're looking at positive values. So reject. And you could stop here. You could say, nope, my observed value is too extreme, quite more extreme than the actual baseline of t star, or the critical value. And so that's it. That's a rejection. However, we're going to take one more step. We're going to actually compute the p-value. So we're going to actually compute, okay, what is the probability that this thing here, this t here, what's the probability that this t here actually happens, or would happen given my null hypothesis, right? So we're going to compute that. And again, for that, I'm going to use a calculator, and it's the same calculator that, again, I showed you during the example. So it's a p-value calculator for t distributions. And again, what I'm going to put here is a t-score. So I'm going to put the 2.44, which is my t-score that I computed there. The degrees of freedom are, again, 21. The significance level is 5. And in this case, it's 5 because I can explicitly tell the calculator to do a two-tailed test. So it's 5 two-tailed, and then calculate. And that gives me a p-value of 0.023641, which is actually the same as approximately 2.36%. Okay, approximately 2.36%. And again, you can see that it's a rejection, because our significance level is 5%, right? And 2.36% is less than 5%. So again, the probability of this thing happening is too low. So I will say here, I can say here that the p-value is smaller than my alpha, which leads to a rejection. And you know, guys, in this case, I represented alpha as 0.05 instead of like 5%, but that's the same, right? 0.05 is the same as 5%, and 0.0236 is the same as 2.36%, okay? So what matters here is that the p-value is less than alpha, and we have rejected our null hypothesis. And the conclusion is, in English, let's say, the conclusion is feud A is not the same as feud B in terms of the size of the tomato plants. So the tomato plants are not the same in feud B. And then you might be tempted to say, because if you look at the actual sample means, you might be tempted to say that feud B plants are larger than feud A plants, right? So you say, okay, they're not different. Oh, sorry, they're not the same, they're different. So obviously one is larger than the other. And if I look at feud B, then I can say, well, they are larger than feud A. So I can conclude that feud B is larger. Plants from feud B are larger than plants from feud A. No. Don't do that, even though that makes sense in your mind. This is not our conclusion, okay? You could make another test, and that would be a one-tail test. And due to being a one-tail test, the critical value would change. But you could do that. You could do a one-tail test if you wanted to test whether feud B is larger than feud A. And I'm not saying that it's not. That's the point here. Look. Actually, I'm gonna go back here, and I'm not gonna cross it out. I'm just gonna actually do it like this. Is it so? I don't know. I can't cross it because I can say that it isn't. But what happens is that I actually don't know, right? I don't know. It could be, but in order to determine this, you would have to run another test, which would be a one-tail test with an alternative hypothesis that feud B is larger than feud A. But I didn't do that, and I won't do that. It can be an exercise for you. I just want to make sure that if you were going to conclude something, this is your conclusion. Okay, the plants from feud A are not the same size than the plants in feud B.